Hello, everyone. My name is Rahman Dusmahamani, and today I'll be presenting our paper, Good Times for Wireless Research. So in a span of only 4 decades, the wireless industry has become a $1+ trillion dollar industry with 7 billion devices connected to the internet. However, all predictions of a next generation wireless usage make these numbers look insignificant as we aspire to wirelessly connect nearly everything to the internet. So the question is, how do we invent this future with the use of scientific research? So the 3 R's of scientific research process are repeatability, replicability, and reproducibility. For repeatability, a research team should be able to repeat their own experiments using their own setup and arrive at the same results. So this is a crucial step in validating that the observed results are not outliers due to random effects, and more importantly, can be explained if reliably repeated. For replicability, a different team should be able to use the same hardware to arrive at the same results as the original team. This is a crucial step for review purposes and ensures no special expertise is required to successfully conduct the experiment. And lastly, reproducibility represents as a different team being able to arrive at the same results using potentially different but equivalent hardware. This last R represents the original concept, elevates the original concept into a scientific principle. So the wireless research community has the luxury to use theory, simulations, and experiments to establish new results. For theory, the 3 R's have always been straightforward. Disclosing all the steps of an analytical result or proofs is a requirement for publishing, which ensures replicability. With the advent of scientific software packages, personal computing, and open source movement, meeting the 3 R's of simulation-based results has also become straightforward. But meeting the 3 R's for experiment-based research remains challenging even today. Repeatability may be the easiest one, but replicability and reproducibility remain challenging. Building a lab capable of reproducing another result is a resource-intensive effort, and comparing against past results is also challenging. This is especially hampered by the fact that there's no rigorous language for describing experiments, and papers also often describe their experiments in a haphazard manner. But why we should care about this? We argue that there are 2 reasons, and these 2 reasons are correctness challenge and amplification loss. Correctness challenge means the review process should check correctness, and for it to be possible, code, data, and analysis associated with the research must be shared. Amplification loss means that if researcher A publishes a theorem, researcher B can understand the details and build on that result, and thereby amplifying the results of researcher A. However, since experiments are challenging to replicate and reproduce, the experiment-based results have a very small amplification factor. So the advent of open source wireless platforms has significantly helped with the amplification loss problem. The open source frameworks such as GNU Radio, Warp Lab, and Open Air Interface allowed many researchers to rapidly build new ideas, leading to thousands of research papers worldwide. In concept, these platforms allowed researchers to partially share an experiment by publishing their code, but still the experimental conditions cannot be shared. Moreover, more experiments are limited to lab settings where the results may not be necessarily applicable in the real world networks. So a shared large-scale wireless testbed could allow us to go beyond repeatability by encouraging the entire research community to replicate and build upon the work of others. They can enable a common language for both the description of the experiments and experimental conditions, and together with open code data and analysis, shared testbeds can enable the much needed research amplification gain that is currently lacking in wireless experimental research. So the Powder Renew testbed is one of the NSF Power platforms, along with Cosmos and AirPaw, which is an at-scale diverse spectrum software-defined radio network deployment. Among many unique elements of Powder Renew, the Renew part of the testbed relates to massive MIMO technology, which is the primary focus of this talk. So this platform realizes the open experiments vision through Powder's shared research infrastructure, as well as open source massive MIMO stacks developed by Renew. A Powder profile defines a specific set of hardware resources, their interconnection, and the code to run on them, which enables sharing and experiment. A statistical repeatability and replicability become feasible by using the same wireless node to validate experimental results. And reproducibility is also made possible by testing on different experiment setups using different base stations and clients on the platform. So the testbed will deploy multiple 64 antenna massive MIMO Renew base stations operating at two key 5G bands, namely 2.5 and 3.5 gigahertz, along with many fixed and mobile client nodes. The base station coverage areas will overlap, while mobile clients can move in and out of individual or overlap cell coverage areas. And to enable coherent receive processing and joint beamforming across all antennas, all base stations will be tightly synchronized both in time and frequency through an optical fiber network and the use of SYNC and PTP protocols. Additionally, Renew base stations are interconnected through fiber to edge compute elements composed of general purpose servers, with each base station supporting 40 gigabit per second front haul. So the key feature of Powder Renew deployment is that it is accompanied with active development of open source software that enable a field operational research radio access network that can be modified at every layer. Given the complexity of the system, the Renew software provides a fast-track development framework with the aim to kickstart massive MIMO research and experimentation by other researchers. So the first framework that is currently available by Renew is called Renew Lab, which provides many STR applications that run in diverse development environments such as MATLAB, Python, and C++, to target various research needs. The second framework is called Agora, which is a real-time software for massive MIMO baseband processing. We will go through both these frameworks in detail in the next slides. So Renew Lab features a real-time measurement software that runs on Ferros hardware. You see it in the picture. Through implementing over-the-air synchronization between massive MIMO hardware and clients, the channel measurement software collects uplink pilots and data from those clients in a configurable manner and generates channel traces for offline processing. The current software supports around 4 gigabytes per second of data recording, and supporting higher rate for handling more antennas at the base station and larger number of users is in progress, which will help in enabling multi-cell channel measurements in a very near future. Renew Lab also includes dataset verification and channel analysis toolbox, which is developed in Python. It allows users to extract useful information from the datasets and gain insights into the performance of the system. The data sets generated by the software are in HDF5 format, which is short for hierarchical data format. Is a format that is widely used in supercomputing applications. It is supported in several programming languages such as C and C++ and Python through open source APIs, and supports metadata and multidimensional data sets, which is useful for massive MIMO, where the number of cells, antennas at the base stations, and users are all dimensions of the data set. Renew also manages a library of channel data sets on Renew website at the address in this slide. Currently, a lot of legacy data sets from older Argos platform are available. New data sets will be available in the very near future in the same website. So Agora is a real-time physical layer processing software developed in C++, running on commodity servers. It addresses the open problem in the ORAN community on the possibility of running massive MIMO on Intel servers. Agora supports real-time massive MIMO baseband processing with a 64 by 16 zero-forcing beamforming at 20 megahertz for both uplink and downlink when run on an Intel 36-core server with AVX512 support. It also includes LDBC encoding and decoding, which is based on Intel FlexRAM library. It is available on GitHub as of earlier this month, and it will be, Agora will appear as a technical paper in Conex 2020 as well. So Renew Lab profile is already available for use on the Powder platform with ample documentation on the Renew website. The documentation provides instructions to use the software and perform experiments for massive MIMO. And Agora profile should be available very soon as well. Overall, we are excited about the future for both the wireless research and wireless technologies using replicable experiments and amplification of experimental research through the shared testbeds, particularly with Powder Renew testbed. Considering the number of ongoing shared testbed efforts, we envisage that performing an experiment will become as simple as sending a link to a paper. Moreover, testbed design itself is becoming a mini research area, and hence there is an opportunity to continue learning as the community gathers more experience in the coming years, which could by itself lead to expanding the existing research testbeds, both in quantity and quality. So that concludes my talk, and thanks for listening, and I look forward to your questions.